Good afternoon everyone present here. So once again I welcome you all for a fourth session of the faculty development program solving of research article using simulation tools. So we move on to the another research article title. So KY converter topology. So KY converter topology is also a DC-DC converters. Move on to the first day session. We discussed about a Shepard-Taylor boost converter. It is also a DC-DC converter. Now, why it is called as a KY converter is the inventor, author initial first letter, they started K, and another one more author initial is YT. So now they started as a first letter of the two authors. Now they framed as a KY converters. That's why it is named as a KY converter topology. So based on the author's initial, so they framed as a KY converter. It is also a DC-DC converter. So it converts for a fixed DC into variable DC voltage. Now again here, how do you form the structure of the KY converter is, so first there is some basic fundamental circuit, KY converter topology. So based on the fundamental circuit, they are going to add the traditional, that is a conventional synchronous rectified based boost converter, buck converter and buck boost converter. So based on that we are going to named as a KY boost converter, KY buck converter, KY boost converter. So there is a separate structure for the KY converter. So it is invented by the authors. Next, KY converter and its derivative, it is developed in the year of 2009. Again the author name is K. Hu and YT Ya. Again next KY converter, next invention KY converter, then next invention second order derived KY converter, then next invention again 2010 KY boost converter, the next invention again two types of KY buck boost converter, next invention voltage gain enhancement of KY converter 2013, 15, 2020, again negative output KY boost converter 2010, the next again novel buck boost converter combining a KY and buck converters 2012 and 2019, the next for FLC come SMC for KY boost converter, myself I developed in the year of 2019, right? So now, so move on to, this is the structure. I already told how do you form the KY buck boost converter, KY boost converter. So initially we need the KY converter structure. So this is the structure of the KY converter. I hope all of you, boost converter structure, a buck converter structure. Here coming to the KY converter, so there is a fundamental circuit, basic circuit for a KY structure. This is the KY fundamental circuit, right? So it consists of the two switches and one diode and three storage elements like L and B and C. So this is the combination. We have some supply voltage. So again we have a two mode of operations. So we have to close the switch. Okay, so then again the input is connected to the circuit. Again the inductor L is store the energy up to the supply voltage. Again this capacitor also going to be charged up to this input voltage. Next again mode 2 we are going to open the switch, right? Then again this is the current flow direction. So based on the inductor current rising and falling, you can use for energy volt second balance equation. Then you will get the ratio of the V0 to Vi, voltage transfer gain is equal to 1 plus D. This is the formula. So this is the basic fundamental circuit. So using this basic fundamental circuit, now they are adding some component like a inductor and again a capacitor and diode combinations. Now we have a KY boost converter. Now this is the fundamental circuit. Just look at the previous circuit. This is the fundamental circuit. This is a fundamental circuit. You need two switches and a diode and a capacitor and inductor combination. Just only adding this inductor and this capacitor. Now they are named as a KY boost converter. Likewise they are adding some component. Based on that we are named as a KY boost converter, buck converter and buck boost converter. So why we go for these type of converters? We have a different types of converters, Cuck converter, Loop converters. If you see the loop converter and the Cuck converter, you have a more number of components, like in terms of storage component, in terms of the device, like switching device and the conduction device, compared to the KY converter. This is the one of the main advantages why we go for this type of topology. Second thing is, KY converter has a continuous input side and output side inductor current. So both the input side as well as for a output side. Next again, we can operate in a continuous conduction mode, and also the ripple voltage. The ripple voltage range is, it is around for millivolt range. So but compared to the our loop converters and Cuck converters. The next one is KY converter has a very good transient response and also quickly settled. So in terms of the millisecond range, that is another one more advantages why we go for this type of structure or topology. Next, it is more suitable for low ripple applications. So next, there is no write of plane 0 when operating in a discontinuous conduction mode. So these are all the main benefit why we go for the KY converter topology. Now I have taken as a one circuit here. Let us take for one paper. This is the KY converter. This is the KY converter. This is a KY negative output boost converter. Again, you have different topology of KY converter. Negative output, positive output KY converter, boost converter, buck boost converter, right? Now I want to design a controller. So this is the one of the structure. So KY buck boost converter. This is the one of the circuit. Now I want to design a controller. So I want to regulate the output voltage of this converter. So what we have to do means, first we have to design for the controller. How do you design for the controller? Let us start for the basic controller, like a proportional integral controller. So how do you design the proportional integral controller? So first you have to derive the mathematical modeling of your converters. So based on the switching on and the switching off period of the converter, you can draw the equivalent circuit during the on time period. Then you can draw the equivalent circuit during the off time period. Then you can apply for a KVL and a KCL to the circuit. Then write down the state space average or state space equation. Then based on the state space equation, then you can form the state space average model. So now in this circuit, so just look at the circuit here. This is the mode 1 operation. In mode 1, just look at the diagram. S1 is on, S1 is on, S3 is on. Now the remaining switch S2 and S4 is off. Now current start to flow from the input positive of the supply, goes to the switch and again go to the capacitor. Capacitor CB is also charged up to the supply voltage. Next again go to the inductor. Inductor also store the up to the supply voltage. Again then go to the capacitor. Then again return back to the supply. This is for a mode 1, right? Then mode 2, again we are going to switch off the S1 and again we are going to switch off for S3. Now then again in the previous mode, so now the input again the capacitor start to discharge again through these S2 and again return back to the supply. Again previous mode the inductor already stored, again it is released, again the capacitor start to discharge again because the inductor supplies the energy to the load. Again the current start to flow from the inductor and again capacitor and load and again return back to the switch, right? So now using this equivalent circuit during the on time period and off time period, now we are going to apply for the KCL. Okay, so apply for KCL and KVL. So how many now here how many number of storage elements are available? Before we are going to form the state variable. State variable means, now just look at the circuit here. You have here 2 capacitors and 1 inductors. So you have a 3 storage element. So for an inductor current, you can take it as a, for inductor you can consider as a inductor current as a variable. Okay. Next, for a capacitor, you can consider as a capacitor voltage as a variable. So first you have to, as before we are going to do the mathematical modeling of modeling using state space average method. So first we have to identify how many number of storage elements available in the circuit. So based on that, you have to assign the state variable. So what do you mean by state variable? Means minimum possible set of variable, so that completely decides your circuit performance. So these inductor and capacitor only decides your circuit working performance. So these variable we are named as state variables. So for a given circuit, you have 3 storage elements. So for inductor, you can represent it as a variable like inductor current, whereas for a capacitor we are going to represent as a capacitor voltage, right? So now let us take for the inductor current is IL as one of the variable. X1 is equal to state variable is equal to IL. Then again you can consider for the CB is another variable, X2 let us take for. Similarly for the capacitor C, you can take for another variable X3, right? Now when we are going to close the switch, so you have to apply for the, this is the one of the loop, closed loop. You can apply for the Kirchhoff's voltage law. Kirchhoff's voltage law. Now what is the voltage across the inductor is, one end of the inductor, so input voltage plus capacitor voltage. Capacitor voltage is also input voltage. So next another end is V0. So now you can write down the state equation during the on time. So this is the on time. I want to write down the voltage across the inductor, L into DIL by dt. So input voltage plus capacitor voltage, one end. So therefore 2V in minus then V0. This is the first equation. We are going to apply for the KVL. So voltage across the inductor, one end is input voltage plus voltage across the capacitor. Voltage across the capacitor is also input voltage. So V in plus V in, 2V in, then one end. Then another end is V0. This. So the potential difference between these two we are going to call it as a voltage across the inductor. So now we are going to write down the first equation. So voltage across the inductor is L into DIL by dt is equal to 2V in minus V0. Next we have to write down the current through the inductor formula. So current through the inductor is IL. Then IL is here you have a node. Now in this node we are going to apply for Kirchhoff's current law. So here the current is entering towards the node is inductor IL. Then leaving current from the node is capacitor IC and again I0. So I0 can be written as V0 by R. Then current through the capacitor we are going to represent as a C into dVC by dt. This is the formula for a current through the capacitor, because we need to find out the derivative of the state variable. So then only we are going to form the state space average model. So therefore, so the next equation, so this is the next equation. So C into dV0 divided by dt is equal to IL minus IC or IL is equal to IC plus I0. Then IL is equal to, you can write down that IC is equal to IL minus V0. I0 can be written as V0 by R, we are going to represent it as a I0. So this is the second equation. So C into dV0 by dt, this is the one of the variable. Let us take for a x3. Upper C into x3 dot. Then here dIL1 by dt we are represented as a IL is a x1 variable. Upper x1 dot. Next another variable is CBE. So now go to the circuit. So in the circuit, so what is the current flowing through the capacitor CB? It is also equal to inductor current. So therefore current through the capacitor formula CB into dVC by dt. So equal to IL. So now we are going to form the next equation. So current equation. So this is the way we are going to write down the differential equation or state equation for during the on time of the switch, right? During the on time of the converter, apply for KVL and KCL. So then you can form the equations. So next we have a 3 storage element. So we are assigned 3 state variable. Now we formed 3 equations. Next during the switch off time period. Again during the switch off time period. So this is the equation. Then again we move on to the equivalent circuit. Now during the switch off time period, just see here, the voltage across the inductor is, here this is plus, this is minus. So the minus is one of the end of the inductor, another end is a plus. So therefore the voltage across the inductor is minus V0. So now you can form the equation. minus V naught during the half time. So voltage across the inductor is L into DIL by dt is equal to minus V naught. Again, next we have to write down what is the current through the capacitor CB. So next, so the current flowing through the capacitor is also equal to input current. So therefore CB into dV CB divided by dt is equal to input current IN. So now you can again write down the, so this is the formula. So input current we can represent as a V in divided by internal resistance of the source, that is the R in. Next you can write down one more capacitor, that is a C, output side capacitor. So in the output side capacitor you can apply like IL is equal to, this is a node, IC plus I naught. So IC can be written as C into dVC by dt, right? Then I naught can be written as V naught by R. Then this is the next equation. So this is the way we are going to form for the state equation. Okay, so once you know the state equation, now we move on to the matrix. We are going to form for the matrix. Then X dot. X dot means here you have a three variable. One is called as a inductor. Inductor is one of the variable, because how do you assign the state variable for your system? System means your converter is based on the how many storage elements available in your converter. Storage elements mean inductor and capacitor. For a given circuit, you have a three storage element, two capacitor and one inductor. So in capacitor, we are going to express it as a variable is a voltage as a variable, state variable. For inductor, we are going to represent as a current as a state variable. So now start from the DIL divided by dt and dVC by VCB divided by dt and dV naught by dt is equal to, now we are going to form for the matrix. Let us take for the A on X dot is equal to A on X is a state variable like IL, VCB and V naught, that is a variable. Then V on and the input V in, and then Y is equal to output matrix C on into X, X variable IL and VCB and V naught, right? Next, just look at the variable here. DIL divided by dt is equal to 2V in divided by L minus V naught by L. So right, so DIL by dt, here there is no IL in this equation. First equation there is no inductor current expression. Next there is no VCB expression, therefore first two variables are 0. 0, 0, IL is also 0, VCB is also 0 in the first equation. So next you have a 2V in divided by L. So 2V in by divided by L minus V naught by L. So minus V naught is the third variable. So therefore minus V naught by L. So minus 1 by L into V naught. If we multiply, so DL by dt is equal to minus 1 by L into V naught plus, coming to the input matrix. So now you have a 2V in divided by L. So now input, so 2 divided by L. So now you can apply the, just apply this expression DI by DL, DIL by dt is equal to, so 0, 0 minus 1 by L into V naught plus 2 by L into V in. So this is the first expression, right? Next, second one, again move on to second variable, dVCB divided by dt is equal to IL by CB. So just again it will become to the denominator IL divided by CB, dVC divided by dt. So now here inductor current is one of the variable, therefore 1 by CB. Then the remaining variable VCB is, there is no VCB, there is no V naught, therefore 0, 0. This is the second equation. Next, third equation again dV naught by dt. So in this expression again IL, so bring into the denominator IL by C minus V naught by R into C. Here you have IL and V naught variable, but you don't have a VCB variable. So VCB variable 0. So the remaining variable is IL by is a first variable. So 1 by C into IL. Next, second variable is 0. Third variable is minus V naught by R. So therefore minus 1 by RC into V naught. So then again you don't have any input matrix. So V in. So therefore 0. So again 0 here. So this is the way we are going to form for the A on and B on matrix, right? So now we move on to, this is a state matrix. Then output matrix here, Y is equal to 0, 0, 1. How do you frame 0, 0, 1 means, here our output variable is here capacitor voltage. So the IL and VCE, it is not output variable. So in the output side, variable is capacitor. So therefore we are going to write the output matrix value 0, 0. Our output side matrix is V0. So therefore 1. Next, off time. Similarly, the same manner we are going to form the matrix during the switch off time period. Then you can take for the average. So A on, A matrix equal to A on into duty cycle plus A off into 1 minus D. Then if you combine these two, you will get A matrix, complete matrix. So this is the complete matrix. So A on into duty cycle plus A off into 1 minus D. 1 minus D is a off time period. 1 minus D into switching time period. So 1 minus D into A off. So A off, this is the A off matrix. This is for B off matrix. Similarly, B matrix equal to B on into D plus B off into 1 minus D. Similarly, for C matrix equal to C on into D plus C off into 1 minus D. Then after substituted in the formula, you will get this is the matrix A matrix and B matrix and C matrix. This is the complete matrix, right? So now you can convert this transfer function also, state space average A matrix and B matrix and C matrix. You can also convert it into transfer function. So this is the way we are going to form the state space average modeling. Okay, next. So how to do the PI controller design? Okay, so first I know the transfer function. Let us take for the transfer function of the system is this is the transfer function. So in MATLAB, you can use for the MATLAB. So let us take for the MATLAB here. I hope you know very well. So let us take for something maybe like, so enter A matrix something. Maybe example I am typing here. So now 1, 2. So, right, next C matrix. You just type for 0 space 1, then D matrix is equal to 0. So next you can form the SYS of some system, SS. So then SS state space A comma B comma C comma D. Right, you will get A matrix and B matrix. Next you can convert for the transfer function. So let us take for SYS some transfer TF is equal to TF into SYS hyphen SS, then enter. So you will get the transfer function, right? So 3S minus. Okay, so you will get some transfer function. Very simple. So you can maybe 3 cross 3 matrix or 4 cross 4 matrix, anything we can just type for the A matrix and B matrix and C matrix and D matrix. Then finally you will obtain for the this transfer function, right? So now this is the model. This is the model. This is the model. So in this model you have to substitute the L value. For example, L value is 200 microhenry, for example. Then duty cycle is 0.5. We are going to choose as a duty cycle is some 0.5. Capacitor value some value. Then R value, load resistance value, you know the maybe 50 ohm. Capacitor another value, some other value. You just substitute, you will get some numerical data. That numerical data you just type in the, this is called the A matrix. Similarly for a B matrix. Similarly next C matrix. Then D matrix 0. Then if you type and then you will get the transfer function. So this is the transfer function. So this is the way we are going to obtain the transfer function. So this transfer function we are going to apply the step response. So now I am going to apply the for a given transfer function step response. So this is a MATLAB result. So from the MATLAB result, it is observed that S-shaped curve actually. So when we are going to apply your model, the model is a transfer function for KY converter. Apply the step input to the system. You can observe your output response. Suppose it is the S-shaped curve. There are methods are available to design for a PI controller. Ziegler-Nichols tuning method. So by using Ziegler-Nichols tuning method 1 and 2, But depending on our response, we can go for a method 1 and method 2. For method 1, suppose your response is S-shape, then we can go for the first method. Suppose your response is sustained oscillation, we can go for the Ziegler-Nichols tuning method 2. Now this is the S-shape curve. So now how to find out that KB value, like P as per the proportional integral controller concern, there are two parameters we have to design. One is called as a proportional gain, second value is a integral value or integral gain or integral time. Now move on to this is the response. So from the output response, so now in the first method, Ziegler-Nichols tuning method, so just this is the S-shaped curve. So take a midpoint, draw the tangent line. Next, from the output response, draw the line towards the Y response. So when the tangent line is cuts towards our Y axis, then again draw one more line towards the X axis. The next again from 0 to up to this center point, the starting point, this is we are going to call it as a L. L is called as a dead time. So during that particular time period, there is no change in the output response. Okay, that particular time interval we express it as a dead time. So time constant T we are going to represent as a time constant. So time taken from the response start from here initial to reach for the final value. So during that particular time period, we are going to express it as a time constant. So take this L value and T value from the response or graph, right? This is the simulated graph. From the simulated graph, you have to take L value and T value. Now in the Ziegler-Nichols tuning method, there are formulas are there. There are some tables are there. Suppose you are going to design for PI controller, there are some formulas. Suppose you are going to design for PID controller, there are some formulas. Now let us take for PI controller, formula is proportional gains equal to 0.9 into T divided by L. So T and L is obtained from the graph. So convert a response graph. Then substitute and find out the values. Next, integral time value, again Ti is equal to, you just substitute like a 0.003 divided by 0.3. So now 0.00 is here T value, I think T value, L value, L by 0.3. The formula is L by 0.3. So now L value 0.005 divided by 0.3. Then you will get this value. So now you know the KB value and TA value. Then we can form. This is the Ziegler-Nichols tuning for suggested table for a method 1. Suppose for P controller T by L. So now PI controller 0.9 T by L. Suppose integral na L by 0.3. Suppose PID na 1.2 into T by L into 2L and 0.5 into L. So this is the way we are going to design for the PI controller, right? I hope all of you clear. This is one of the method. Suppose you have a sustained oscillation, then there you can follow for the method 2. Next. Come photo எடுத்துக்கலாம் நீங்க நான் அனுப்பி விடுற மெட்டீரியல் விடுங்க எடுத்துட்டீங்களா ஆமாம் எடுத்துங்க தெரியாது பட் சரி ஓகே எடுத்துட்டேன் ஓகே நெக்ஸ்ட் ஸோ நவ் வி மூவ் ஆன் டு த ஸோ நவ் திஸ் இஸ் த another circuit. Okay, so this is the another circuit, same converter, but it is a negative output KY boost converter. This is another topology. So you have a more number of circuits are available for KY or so many KLU converter. Okay, so now for the given circuit, so I simulated. So just take for the source, then again MOSFET and capacitor, inductor. So now feedback, I want to regulate the output voltage. I am going to take the feedback from the output side. Here I am going to mention as a minus 12 volt as a reference voltage. This is the PI controller. So outer loop, inner loop I am going to use for a P controller for regulating the current. Then this is for a triangular. You know very well how to form the triangular. So now you know the switching frequency, then find out time period, then form the triangular. Relational operator we have to compare and generate the pulse applied to the switch. Now here I am going to represented here minus 12 volt as a reference value. Now just see here, your output voltage is going to be settled for a minus 12 volt. So it is going to be settled for a minus 12 volt. So even I am going to changing some input voltage, like let us take for 7 volt. So now I am changing the 7 volt. Just see here. Then output is again settled. So output is settled here. So this is called a line variation. This is called a line variation. So I am changing the input voltage. The output is again maintained constant by using a controller. You can change the load also. You can change the reference value also. So now we are going to regulating the output voltage by using a PI controller. So just see here, our reference value is minus 12 volt. So whatever the value we are set in the reference voltage, the same value we are going to obtain at the output side. So now minus 12 volt. Now we are changing the input voltage. Then again the output is settled, but there is some peak overshoot and settling time. If we go for other type of controller, fuzzy or neural or other type of controller, we are going to minimize this peak overshoot. We are going to minimize this peak overshoot, and we are going to quickly settle the response. So we can compare the other, maybe this is the conventional controller. Then you can also go for some proposed controller. For comparison purpose, first you can start for the proportional integral controller. Now let us take for here minus 15. So I am going to set my reference voltage is minus 15. So now let us take this is for 5 volt. Now I have to check for all the operating conditions. Now here the reference value is we are settled for the minus 15. Now again it goes to the minus 15. So it is going to settle for the minus 15. So our reference value minus 15. The output also going to be settled at minus 15. So I already told what is the main advantages for this KY converter is minimum ripple voltage. You just stop the simulation, then double click, then zoom for a Y axis. So you can observe here somewhat minimum ripple. So it is a minimum ripple. So it is always millivolt range. So very small value of ripple. You can compare to the y-axis magnitude. So I hope all of you clear. So can you construct the circuit? Do it yourself. Can you all of you construct the circuit? Okay. So take the component. It is available. I hope all of you know. I hope how to take all the component. Just use the MATLAB. So construct the circuit first. Okay. First. Hello. Hello. இதை கன்ஸ்ட்ரக்ட் பண்ணுங்கப்பா எல்லாரும்